Hi, my name is Daniel Odamelum, and this is Project 3.4.1, SAR ADC, Clock, and Overview. The Successive Approximation Register Analog to Digital Converter, or SAR ADC, translates an analog input to a digital binary representation. This here is the inverter-based clock circuit comprising of a 74HZ04 hex inverter, two 510 ohm resistors, and two 0.1 microfarad capacitors. This is the clock that will be used for the 7-bit SAR ADC as initially made by Mitsuru Yamada. Yamada claims that this clock has a frequency of 10 kHz, which can be confirmed with its reading on an oscilloscope and through some math. Here we have tau equals RC, and so tau is a time constant, and in this circuit for the clock we have two resistor capacitor networks, so tau therefore equals 2RC in this case. And by using tau as the time constant for the frequency equation, we get frequency equals 1 over tau. And by subbing in our values for the resistor and capacitor, we get 1 over 2 RC, and we get our frequency is 9.8 kilohertz, which is very close to the originally proposed 10 kilohertz. Moving on to the overview of the SAR ADC, this is its circuit diagram. How it works is that once voltage enters the circuit here at the analog input, it goes into the sample and hold IC. This chip temporarily freezes the voltage and charges the holding capacitor to ensure that the voltage doesn't change during the conversion, which would otherwise result in an incorrect binary representation. The main parts of the SAR ADC here we have are the R2R DAC and the D flip-flops. The D flip-flops here are clocked successively, meaning this one's clocked first, second, third, and so on and so forth. When clocked, these flip-flops that are preloaded with the 1 outputs a 1 here on the DAC. So for example, on the first clock, this flip-flop is clocked and then puts a 1 here on the DAC, which is read out as 1 0 0 0 0 0 0 for these 7 bits. And this translates to a DAC output with an analog voltage of Vref over 2. What happens next is that is fed here into the comparator, which compares the input voltage with whatever is outputted from the DAC, and if it is higher, it outputs a 1, which goes to the data pin of the flip-flop, meaning it retains its 1, and if it's lower, if the input is lower than Vref over whatever it is, it clears this bit and then moves on to the next flip-flop. This process is then successfully repeated for all 7 flip-flops. So, for an example calculation, if we had a reference voltage of 5 volts and we had 3.6 as our input volts, what happens here is you have 3.6 here, you'd have 5 volts over 2 as your first one. So 5 volts over 2 is 3.6 greater than 2.5, yes, so you'd have a 1. Then you now second flip-flop gets clocked. Is it greater than 5 volts over 2 plus 5 volts over 4, which is 3.75 volts? No. So you'd have a 0. Is it greater than 5 volts over 2 plus 5 volts over 8? Yes, it is. It's greater than 3.125, and so on and so forth, until you eventually get your answer of 1 0 1 1 0 0. So the binary representation of 3.6 volts with a reference volts of 5 volts from the 7-bit SAR ADC would be 10111100. My name is Daniel Odamelum, and thank you for listening.